There is something in physics so terrifying that some scientists refuse to discuss it publicly. It is not a black hole. It is not a gamma ray burst. It is not an asteroid. It is the possibility that right now, this very second, a bubble of destruction could be racing toward Earth at the speed of light. We would have no warning, no time to react, no way to know it was coming. And when it arrived, it would not just destroy us, it would erase us, erase the planet, erase the sun, erase every atom, every law of physics, every possibility of existence as we understand it. It is called vacuum decay, and according to our best measurements of fundamental physics, the universe may be sitting on a trigger. What you're about to learn is not science fiction. It is the logical consequence of equations that describe reality at its deepest level. And the most disturbing part, there is nothing we could ever do about it. To understand why vacuum decay is so terrifying, we need to understand what physicists mean by vacuum. In everyday language, a vacuum is empty space, the absence of matter. But in quantum physics, a vacuum is anything but empty. It is a seething ocean of energy, filled with fields that permeate all of space and time. One of these fields is the Higgs field. You may have heard of the Higgs boson, the particle that won the 2013 Nobel Prize and was detected at the Large Hadron Collider. The Higgs boson is a ripple in the Higgs field, and that field is what gives particles their mass. Here is the crucial part. The Higgs field has an energy level. Right now, throughout the entire universe, as it sits at a particular value, about 246 gigaelectronvolts. This value determines the masses of fundamental particles, the strength of forces, and essentially all of chemistry and physics as we know it. The question that haunts physicists is this: is this the lowest possible energy state? Or are we sitting on a false floor? Imagine a ball resting in a small crater on the side of a mountain. From the ball's perspective, it is at the lowest point it can reach. It cannot roll anywhere without first going uphill. It is stable, safe, but there is a deeper valley at the bottom of the mountain. If something could give the ball enough energy to escape the crater, or if it could somehow tunnel through the crater's wall, it would roll all the way down to the true lowest point. This is the concept of a false vacuum versus a true vacuum. A true vacuum is the absolute lowest energy state possible. A false vacuum looks stable, but is actually just a local minimum, a temporary resting place above the true ground state. In 1979, physicists Sidney Coleman and Frank DeLucia calculated what would happen if our universe existed in a false vacuum and then decayed to a true one. The result was not comforting. If a transition occurred anywhere in the universe, a bubble of true vacuum would form. Inside this bubble, the laws of physics would be different. Particles might have different masses, forces might work differently, and atoms as we know them might be impossible. The bubble would expand outward at the speed of light, converting all false vacuum into true vacuum as it spread. Everything the bubble touched would be rewritten at the most fundamental level. Not destroyed in the usual sense, unmade. For decades, this was a theoretical curiosity. We did not know whether the Higgs field was in a true vacuum or a false one. Then, in 2012, scientists at CERN discovered the Higgs boson and measured its mass, approximately 125 gigaelectronvolts. When physicists plugged this number into their equations, they got a troubling result. The Higgs field appears to be metastable, not in a true vacuum, not in an obviously unstable configuration, but balanced on a knife's edge between the two. Think of it like a pencil balanced on its point. It is technically stable, but the slightest perturbation could send it falling. Our universe seems to exist in a similar state, stable enough to have lasted 13.8 billion years, but perhaps not stable forever. According to calculations, if the standard model of physics is correct, and there is no new physics beyond it, the Higgs field's current value is not the lowest possible energy. At very high energies, around 10 to the 12 gigaelectronvolts, the potential turns over and becomes negative, suggesting a deeper valley exists below. This means vacuum decay is not just possible, It may be inevitable. The only question is when. If vacuum decay occurred, it would start with quantum tunneling. At any point in space, at any moment, there is an infinitesimally small probability that the Higgs field could spontaneously tunnel through the energy barrier, separating our vacuum from the true vacuum. A tiny bubble of true vacuum would nucleate, form out of nothing. The probability is staggeringly low. Calculations suggest it might happen once every 10 to the 100 years. That is a 1 followed by 100 zeros, a number so large that the current age of the universe is a rounding error by comparison. But here is the terrifying part. If it has already happened somewhere in the universe, we cannot know. The bubble expands at the speed of light. Information about its existence also travels at the speed of light. This means the bubble and the news of the bubble arrive at exactly the same moment. There is no warning, no detection, no advance notice. One moment, you exist. The next, you do not. There is no pain, no experience of destruction, or because the processes that create consciousness would be erased faster than neural signals can travel. Let us be clear about what would happen inside the bubble. This is not an explosion. This is not fire or radiation or any kind of destruction we can imagine. It is something far stranger and more absolute. Inside the bubble, the Higgs field would have a different value. This means particles would have different masses, or perhaps no mass at all. The electron might become thousands of times heavier, or it might vanish entirely as a stable particle. The forces that hold atoms together would change. Chemistry would stop working. The atoms in your body would not just fall apart, they would become physically impossible configurations. Stephen Hawking once described vacuum decay as the ultimate ecological catastrophe. In the new vacuum state, not only would life be impossible, but the very concept of matter, as we understand it, might cease to exist. The physicist Sidney Coleman put it more starkly. He calculated that if a bubble of true vacuum formed near our location, the resulting universe inside would collapse to a singularity in a few microseconds. Everything that ever existed would be compressed to a point and erased. The spontaneous probability of vacuum decay is extremely low. But what if something could trigger it? In principle, an extremely high-energy event could kick the Higgs field over the barrier into the true vacuum state. This raised concerns when the Large Hadron Collider was built. Could particle collisions at unprecedented energies nucleate a vacuum bubble? Physicists studied this question carefully and concluded, no. Cosmic rays, particles traveling through space at near-light speeds, regularly collide with atoms in our atmosphere at energies far higher than anything the LHC produces. These collisions have been happening for billions of years, all over the universe, and no vacuum decay has been triggered. But there are other scenarios. Some physicists have suggested that primordial black holes, tiny black holes theoretically formed in the early universe, could serve as seeds for vacuum decay. As they evaporate through Hawking radiation, the extreme conditions near their event horizons might provide enough energy to trigger a transition. Others have pointed to cosmic inflation, the rapid expansion of space in the early universe, as a period when the Higgs field might have been pushed dangerously close to the edge of stability. The fact that we exist suggests either that our vacuum is more stable than calculations indicate, or that we got extraordinarily lucky. Here is a strange comfort in the terror. If vacuum decay has already begun somewhere in the universe, the bubble might never reach us. The universe is expanding, not just the galaxies moving apart, but space itself stretching. Beyond a certain distance, the cosmic horizon, space is expanding faster than light can travel through it. This means that if a vacuum decay bubble nucleated in a distant galaxy, and that galaxy is receding from us faster than the speed of light due to cosmic expansion, the bubble can never catch up. It would be expanding at light speed through space, while space itself carries it away from us faster. In an infinite universe, vacuum decay might be happening constantly, and in countless locations, bubbles spreading through space, and yet we might never intersect with any of them. But this is cold comfort. The bubble does not need to form in a distant galaxy. It could form anywhere. It could form in the space between galaxies. It could form in the space between here and Alpha Centauri. It could form right now closer to Earth than the Moon. Before we despair, let us consider the reasons physicists are not losing sleep over vacuum decay. First, the calculations that suggest metastability depend on the Standard Model being complete. Most physicists believe there is physics beyond the Standard Model. New particles, new forces, new phenomena we have not yet discovered. These could stabilize the Higgs field completely. Supersymmetry, for example, if it exists, would add new particles that contribute to the Higgs potential and could shift the field from metastable to absolutely stable. Other extensions of the Standard Model have similar effects. Second, even if the universe is metastable, the timescale is almost unimaginable. The estimated lifetime before decay is something like 10 to the 100 years. The current age of the universe, about 14 billion years, is nothing by comparison. On those timescales, protons might decay, black holes might evaporate, and the universe might reach heat death long before vacuum decay occurs. Third, the fact that we exist is evidence. If vacuum decay were highly probable, it would likely have happened already in the 13.8 billion years since the Big Bang, or during the violent conditions of the early universe. The very existence of a stable cosmos around us suggests either that our vacuum is more stable than calculations indicate, or that the conditions for triggering decay are rarer than feared. Vacuum decay is not the only threat lurking in the cosmos. Let us briefly survey the competition. Gamma-ray bursts. When massive stars collapse or neutron stars collide, they can release more energy in seconds than the Sun will produce in its entire lifetime, focused into narrow beams of gamma radiation. A burst aimed at Earth from within a few thousand light years could strip away our ozone layer and trigger mass extinction. Some scientists believe a gamma-ray burst may have caused the Ordovician mass extinction 440 million years ago. Rogue black holes. Approximately 100 million stellar mass black holes wander through our galaxy, invisible remnants of dead stars kicked into interstellar space by supernova explosions. If one passed through our solar system, it could disrupt planetary orbits and fling Earth into deep space or into the Sun. Magnetar flares. On December 27, 2004, a burst of energy from the magnetar SGR 1806-20, a neutron star with an unimaginably powerful magnetic field, hit Earth from 50,000 light-years away. In 1/10 of a second, it released more energy than our Sun produces in 150,000 years. It was bright enough to ionize our atmosphere and disrupt radio communications. Had it been within 10 light-years, it could have caused mass extinction with strange matter. A theoretical form of matter called strangelets could, if they exist with certain properties, convert ordinary matter into strange matter on contact. A chain reaction that could theoretically consume the entire Earth in seconds, leaving behind a ball of quarks 100 meters across. Why does vacuum decay feel different from these other threats? Perhaps because it represents something deeper. A gamma-ray burst would kill us, but it would leave the universe intact. A black hole might destroy our solar system, but somewhere else, life could go on. Even a strange matter event, as horrifying as it sounds, would be local. Vacuum decay is different. It would not destroy things within the universe. It would rewrite the rules that make the universe possible. It is not a disaster that happens in reality, and it is a disaster that happens to reality. There is something almost religious about this threat. It suggests that existence itself is contingent, that the ground we stand on, the laws that let atoms hold together, and thoughts form and love exist, are not guaranteed. They are a configuration, an arrangement, and arrangements can change. Philosophers call this modal fragility, the sense that things could be radically, unrecognizably different. Vacuum decay makes that possibility visceral. And yet, here is what I find most remarkable. We are here. The universe is 13.8 billion years old. It has survived the violence of the Big Bang, the chaos of inflation, the bombardment of cosmic rays, the deaths of billions of stars, the collisions of countless galaxies. Through all of it, the Higgs field has remained in its current state. Either our vacuum is more stable than our calculations suggest, which means there is physics we do not yet understand that protects us, or we have been astonishingly, incomprehensibly lucky. But here is a different way to think about it. In an infinite universe, or a multiverse with countless different regions, vacuum decay might indeed be happening constantly. Bubbles of true vacuum might be nucleating and expanding all the time in countless locations, erasing everything they touch. But we could never observe those regions. By definition, if vacuum decay happened in our observable universe before now, we would not be here to ask the question. The very fact that we can contemplate vacuum decay is evidence that it has not happened yet, at least not close enough to reach us. Our existence is not an argument that the universe is safe, but it is an argument that this particular corner of it, this particular history, has been stable long enough for consciousness to emerge and wonder about the nature of reality. So what are we to do with this knowledge? We cannot prevent vacuum decay. We cannot predict it. We cannot prepare for it in any meaningful way. If it comes, we will not know. Perhaps that is the strangest kind of peace. There is no anxiety to be had about something so absolute, so fast, so final. It would not be an experience of ending, it would simply be an ending. And if it never comes, if the universe truly is stable or metastable for timescales beyond comprehension, then we have been given something extraordinary, a cosmos that holds together, laws of physics that permit atoms and stars and minds. Time to think, to love, to wonder. The ancient philosophers asked why there is something rather than nothing. Vacuum decay reminds us that something is not guaranteed, that existence is not a given, that the very fact of being is, in some sense, a gift, or at least an improbability vast beyond measure. Tonight, when you look up at the stars, you are looking at a universe that has held together for billions of years. Every photon that reaches your eye is evidence that reality, at least along that line of sight, has remained stable. We exist in the interval between creation and potential collapse. It may be an interval of 10 to the 100 years. It may be eternal. Either way, we are here now. And that is something.